Okay, so let's begin with some basics. So if you're talking about quantum gravity in flat space, then the most basic observable you have is the S matrix, which is just scattering of two gravitons in and then two gravitons out. So by quantum gravity, I of course mean string theory, because there's no other. So for instance, in 10-dimensional string theory, the S matrix is computed from the world sheet in an expansion in the genus. And originally the answer is for finite string length, but then you can of course then expand it furthermore to get an expansion also in string length. The other theory of quantum gravity, which is related, is M theory, which naturally lives in 11 dimensions. In this case, the S matrix is only expanded in Planck length because there's no strings. So there's no dimensionless parameter, there's just the one dimensionful parameter of Planck length, which you can also think of as a small momentum expansion. Because there's no world sheet, there's no independent way of computing this amplitude, and so in practice, only the lowest few terms are known by relating them with dualities to known string theory amplitudes. Yeah, but I think it's hard to compute a lot of things with that method. I don't know that much about it, though. So you can think of this graviton S matrix just as like a usual S matrix, and so we have two gravitons in, two gravitons out, and then the expansion I was describing, the leading order term comes from a vertex from the Einstein-Hilbert term, which is R, and then because 10 or 11-dimensional supergravity, of course, is not renormalizable, and so there's going to be infinite higher derivative corrections, which you can think of as covariant derivatives D with various powers acting on R to the 4, and these are all dictated in principle by string theory and M theory, which are ultraviolet completions of supergravity. And then there's also loops, which I'm not writing. And so for all these higher derivative corrections, they're going to come with higher and higher powers of the dimensionful constant, which in M theory is the Planck length, and in string theory we can think of as string length. Okay, great. So the way we're going to be studying these is by relating them to CFT. So the basic statement of ADS CFT is that if you take a theory of quantum gravity, if you compactify it on ADS D plus 1 times some compact manifold, then this is going to be dual to some supersymmetric CFT in D dimensions with n colors, because generically these are always gauge theories. So, and then, in particular, if you then take the large n limit, it's expected that the D-dimensional CFT is going to be dual to some weakly coupled supergravity on ADS D plus 1, where all the higher derivative corrections to supergravity should in principle be determined from string theory or M theory, which are the ultraviolet completions. So the examples I'm going to consider in this talk are the most famous ones. So for instance, M theory on ADS4 cross S7 mod ZK is dual to the 3D CFT called ABJM theory, which has two gauge groups, each with the Chern-Simons level. And in this duality, n k is small. Another dual of ABJM theory is type 2a on ADS4 cross CP3, in which case n and k are both large, and the Tuft coupling, which is roughly n over k, is fixed. And then you can furthermore send lambda to infinity if you want it to be weakly coupled. And then the other duality is the original one, which is type 2b on ADS5 cross S5, dual to 4-dimensional SUN Supergang-Mills at large n. So in all these cases, we're going to relate the quantum gravity S matrix to an amplitude on ADS D plus 1, which is holographically dual to a 4-point function of single trace operators in CFT. So this is just the basic statement of ADS CFT. And so we're going to be studying these single trace operators in CFT and then use ADS CFT to then relate it to these ADS amplitudes and then take a flat space limit to get these S matrices. Okay, so let's give the plan in a little bit more detail. So first we're going to do super symmetric Gang-Mills, then we're going to do ABJM theory. So the first step we're going to do is we're going to fix the functional form of these large n CFT correlators, which can be equivalently thought of as ADS D plus 1 amplitudes. And this is just going to be based on superconformal invariance and some constraints from the existence of a flat space limit. So we're not going to use the Lagrangian at this point. So this is very general. In the next step, we're going to use the Lagrangian. In particular, we're going to use formulas for the massive form free energy, which can be computed from the Lagrangian using localization to fix the coefficients of these terms in a large n expansion for the lowest few terms. And then finally, we'll take the flat space limit using Joao's formula, and we're going to compare to quantum gravity in 10 or 11 flat dimensions. And so you can go both ways. Either you can start with CFT and use this to rederive S-matrix terms. So like imagine you didn't know what they were, now you would know the answer. Alternatively, you can use the known answer, because people have computed many terms in these S-matrices, to further constrain the CFT correlator. So if you're someone who only cares about CFT, you would be interested in the second method. If you're someone who cares more about quantum gravity, you would be interested in the first method. And we're going to have new results in both. Yes? So only at low orders. Yeah, so that's a good question. I'm going to discuss this later. So yeah, so let's just table that until later. But like, yeah, in general, no, because there's only one expansion parameter. But at low orders, coincidentally, yes. Okay. So let's review some known properties about these S matrices before we continue. So we'll start with the type 2B S matrix. So this is known to 2 loops due to this incredible calculation by Doker and Fong, which they did from the world sheet. We write the answer like this. So this AR term is just the supergravity term. We're just factoring it out. So that takes care of all the polarizations. We don't have to worry about it. And then here we are expanding it in the string length and the string coupling, as described before. ST and U are just the usual Mandelstam variables. And I colored this one in green because it's going to be a little important later on. And so just to note, the powers of string length are basically just determined from dimensional analysis. And so it turns out that a vertex corresponding to d to the n minus 6 r to the 4 will correspond to have a coefficient of string length to the n. And then this term in green, which I've been highlighting, so this regulates a quadratic divergence, which would show up at one loop, because of course, you know, supergravity is not a renormalizable theory. And this is something which you learn from string theory. So if you didn't have string theory, you would just be stuck. You would have a divergence. You would have nothing to do. But because of string theory, you do a genus 1 calculation and you compute this quantity. So this is a non-trivial prediction from string theory. There are other terms that also show up at one loop, which are non-analytic in the Mandelstam variables. They involve logs. And these terms can all, in principle, be computed just from tree level using unitarity. So in a sense, they're not really genus 1 terms, because you can get them from genus 0. Okay, so far I looked at one limit, which is the limit where you're doing an expansion for small string coupling. But it turns out you can do something even more, which is you can actually, for the lowest few protected terms, in terms of string length, you can compute them for any string coupling, using the fact that 10D string theory has this S to Z duality group. So this was done in a bunch of papers by Green and various collaborators. So they were able to do this just for these terms. These are the protected terms, so r to the 4 all the way up to d to the 6 r to the 4. The answer is in terms of these Eisenstein series, which is like the curly E. I also show what happens when you expand them. So you get like the usual perturbative terms in GS, but then you also get an infinite number of these non-perturbative terms, which I didn't write explicitly. So notice that the one in green is the same one in green from the previous slide. And I just didn't go up to these higher orders in GS, otherwise you would have seen the one in blue as well. So these are just the analytic terms. And as usual, the non-analytic terms can be determined from these just using unitarity. So you can always get non-analytic terms from tree level. Okay, great. Yeah? So because there's 2 ways you count things. So there's the string length and the string coupling. So string length counts higher derivative corrections. So for instance, r to the 4, d to the 4, r to the 4, et cetera. But it doesn't care about loops. And G string counts loops, but it doesn't care about higher derivatives. So in this expansion, it's kind of like finite order for loops. So it's almost kind of like a infinitely quantum answer. But it's still an expansion in string length. I mean, the reason why we're able to do it is because this is a protected term. So just these 3 terms are protected due to supersymmetry, and that's why this kind of miracle occurs. Like, once you go beyond these terms, complete hell would break loose. And, like in a sense, it's like as if you were able to do a world sheet calculation and compute every single infinite term in the world sheet, you would get this answer. Yeah. Okay, great. Okay, so now let's move on to type 2A and the M-theory S matrix. So perturbatively, it turns out that type 2A is actually the same as type 2B for all the terms that have been computed so far. This isn't expected to be the case at all orders, but just at the up to 2 loop and even some 3 loop that people have computed, they're just the same. This also wouldn't be the case for higher point functions. This is just perturbatively. Of course, non-perturbatively, type 2a is not S-duality invariant, so you don't expect to get these Eisenstein series or any of these exponential terms. So, but we're just going to talk perturbatively here. And then, of course, the way M theory was discovered is that it is the S-dual of type 2a. So if you take 10-dimensional type 2a, then you can relate it to M theory in 11 dimensions, where you have one of the dimensions compactified on a circle, then you make the circle really small, and that's how you go down to 10 dimensions. And in particular, the mapping between the parameters is that the string coupling is related to 11-dimensional Planck length and this radius like that, and similarly for the string length. And so for protected terms, and only for protected terms, so i.e. the terms in the previous slide, you can just perform this change of variables and then like set R11 going to infinity to go from type 2a to M theory, and the terms that survive, those are going to be the answers in M theory. And so this is why I was coloring these in colors before, so you could remember them. So it turns out that the one loop R to the 4 guy ends up being the tree level R to the 4 guy now in M theory. Similarly, the 3 loop D to the 6 R to the 4 guy becomes the tree level D to the 6 R to the 4, whereas D to the 4 R to the 4, it just didn't have the right powers of G string to survive. So after you take this limit of radius going to infinity, it just dies. So this is actually kind of a non-trivial prediction of these dualities, which is that there is no D to the 4 R to the 4 tree level term in M theory. It would have been allowed by supersymmetry. So if you just looked at the allowed counter terms, it would have been allowed, but it's not allowed from this construction. Okay, so now we're done with the review of these S matrices, and we're going to move on to the CFT calculation. So let's begin with n equals 4 super Yang-Mills. So the way it's defined, it's an SUN gauge group. It could actually have any compact gauge group, but we're going to focus on SUN. It's a conformal manifold, which is parametrized by tau, which is the complexified coupling, and its duality group is SL2Z. So the R symmetry is SU4, and also if you look just at the 4-point function, there's a bonus U1 symmetry, which doesn't exist in general, but organizes 4-point functions. It turns out it's actually more convenient, instead of thinking of large n, to think of large CT, where CT is the coefficient of the stress tensor multiple 2-point function. This is the more natural parameter for holographic correlators. For n equals 4 super Yang-Mills, the relation is quite trivial because C is in fact just the conformal anomaly and is fixed basically to be like the dimension of the group. Okay, so you don't have to carefully study this table. It's very complicated. The only ones you should really pay attention to is the bottom component, which is a dimension 2 scalar S. Then there's another scalar, P, which is in fact complex, which has dimension 3. And then there's a third scalar in the stress tensor multiplet, which is the marginal one, which is also complex, which is phi. And so S, P, and phi are going to be the 3 heroes of the story. The other ones were used in the calculations, but you won't have to worry about them so much. Okay, great. So now let's describe its ADS-CFT dual in a little bit more detail. So it's dual to type 2b string theory and ADS5 cross S5, and we relate the CFT parameters to the quantum gravity parameters as following. So the string length is naturally related to the tuft coupling, which we define here to be n g Yang-Mills squared. And then the string coupling is very trivially related to g Yang-Mills. So at large n, it should be dual to weakly coupled supergravity on ADS5 cross S5. And in particular, after taking this tuft limit, if you make lambda go to infinity, then you get weakly coupled supergravity. And so this is how you relate the expansion and CFT parameters to the expansions you saw before on the string theory side. So C is counting loops, and lambda is counting higher derivatives. So if you just want to look at tree level, everything's going to be 1 over C, but then you're going to have all these corrections in lambda. Alternatively, you could just look at supergravity, but go to higher loops, and there would be bigger powers of C. When you look at this expansion, you don't see the SL2Z invariance, because SL2Z invariance has to do with transforming G Yang-Mills, but now you're basically taking some weird limit where it's like infinity. So you wouldn't see it term by term. So this is related to the expansion. It turns out there's another interesting expansion, which isn't as spoken of, but it's also interesting, which is that you make n go to infinity, but you keep G Yang-Mills fixed. The reason why this expansion is nice, I mean, it's also a holographic expansion, so you can also understand it geometrically. The reason why it's nice is that now that G Yang-Mills is fixed, the terms in this expansion should be SL2Z invariant. In this case, there's only one expansion parameter, which is C, and so it has to count both loops and higher derivatives. So like with Shota's question, like how do you distinguish them? So in general, you can't. But at very low orders, they're just going to have different powers. So it's going to happen that the higher derivative corrections are going to have some weird fractions, whereas loops are going to be integer powers, and that's how you're going to distinguish them. In the flat space limit, this corresponds to the finite G string expansion. So the one where you saw those Eisenstein series. So that's the bulk version of this CFT limit. Okay, so now let's go into more detail. So we're going to be studying the 4-point function of the 20 prime operator, which was discussed today already. Just based on conformal symmetry, you can write it as a function of u and v, where you factor out these powers. These are the usual conformal cross ratios. And then a formal solution to the ward identity, derived by Dolan and Osborne, is that you can write the full 4-point function as a free part plus some simple polynomial in u and v that soaks up all the R symmetry indices. And then the non-trivial part is this function t of u and v. This doesn't depend on R symmetry anymore, and this has all the dynamical information in the theory. And so that's the quantity we're going to talk about. So I'm also going to be using Mellin space, like in previous talks. This is the basic definition of a Mellin transform of this quantity. So you go from position space u and v to Mellin space s and t with these gamma factors. So st and u equal 4 as usual. And one thing to keep in mind is that poles in st and u correspond to dimensions of operators, which basically follows from this formula. This formula is basically a Fourier transform from s and t space to u and v space. And so just based on the definition of the Fourier transform, like the dimensions are like the Fourier version of poles. Okay, so let's set down some notation. So for the full Mellin amplitude, which is the transform of this t, we're going to write it as a sum over these MPs, where I define MP such that they are degree p minus 4 when I make s and t go to infinity. The reason why I'm doing minus 4, which can be a little bit confusing, is because I'm looking at the reduced amplitude. If I would have been looking at the full amplitude, like the one which has R symmetry indices, then this would be degree p. So that's the explanation for this notation. And then this wonderful formula by Joao says that if you take a Mellin amplitude with the degree p, and I'm just normalizing by the supergravity guy. You don't have to do that. This is just for simplicity. Then when you take the flat space limit, this is related to a term in the S matrix which has 2 p derivatives. So, and with this important p-dependent factor. So for instance, if you were looking at M1 itself, then that it corresponds to a 2-derivative term in the S matrix, which is, of course, the Einstein-Hilbert term. And then if you want to look at higher derivative terms, such as r to the 4, then you look at higher degree Mellin amplitudes. So let's see what general constraints we have on Mellin amplitudes without knowing anything about the specific theory. So this is just very general. This has nothing to do with n equals 4 super Yang-Mills. So we have crossing symmetry, which is trivial in this case. You just exchange st and u. And then if we're concerned only with tree-level correlators, then we know that only single and double trace operators should appear in the OPE. And the gamma functions automatically take into account double trace operators. Like, that's why they're there. I mean, in a sense, this is a definition. And the reason why we use that definition of the Mellin amplitude is that we don't have to worry about double trace operators. Their poles are at precisely the values where double trace operators would be. So this means we only care about single trace operators. And for large N holographic theories, what's very nice is that there are very few single trace operators. In particular, there's only the operators in the stress tensor multiplet. So there's only 3, which is like a scalar, a vector, and a graviton. This has to do with the fact that you have a consistent truncation to just supergravity. So you don't have to keep any higher half BPS guys. Okay, great. So when you use just these 2 constraints, it turns out it's extremely constraining. And so the allowed Mellin amplitudes of degree p are given by this table. So on the first row, we write the quantum gravity vertex it's going to be related to in 10 dimensions. On the second row, we say how each coefficient in the CFT would scale in the strong coupling limit. So as you see, higher derivative corrections get higher and higher powers of inverse lambda, whereas it's always the same power of 1 over c, because it's all tree level. And then the very strong coupling limit, which might be a little bit less familiar, now there's only one expansion parameter, c. And so, as mentioned before, these higher derivative terms in low orders can be distinguished from loops because they have these weird fractions, whereas higher loops would have integer powers. So like if you see minus 7 over 4, you know that it's r to the 4. But if you were to look at some super high term, you wouldn't necessarily know. Lastly, and most importantly, the bottom line says how many possible Mellin amplitudes there are of this degree. So there's only one of degree 1. There's a new one we find at degree 4, so there's a total of 2. Then we find another new one at degree 6, another new one at degree 7. So this is very constraining, because a priori, before you impose crossing symmetry, there's like hundreds of them, but now you're only left with basically one new one at each order, at least to this low order. So in particular, M1, which was computed by Joao and probably other people, so this corresponds to the stress tensor multiplet superblock, and in fact, M1 includes all the single trace poles, because it's related to the stress tensor multiplet superblock. And so this means that there's not going to be any poles for anything beyond M1, because we've already used up all the poles for M1. So that means all the higher MPs are just going to be pure polynomials of degree p. Also, the coefficient of M1, just based on conformal word identities, is related to C. So that means we've already fixed one coefficient. And so that means to get higher coefficients, we now only need a few parameters to be fixed. In particular, the precise form was originally given by Alde and collaborators. So in particular, we're going to need one constraint to fix the r to the 4 guy. We would need two constraints to fix d to the 4, r to the 4, et cetera. Three constraints for d to the 6, r to the 4. So now we've just discussed general holographic theories. Now we're going to move on to specifically n equals 4 super Young-Mills by using localization in order to actually fix these coefficients to get these higher derivative terms. So the localization quantity we're going to use is the massive form free energy. So consider the n equals 2 star theory on S4, which is where you deform super Young-Mills by hypermultiplet mass. So you can take the n equals 4 Lagrangian, and you can add the following mass deformation, where j and k are dimension 2 and 3 operators. This is an n equals 2 language. If you were to relate this to n equals 4, then j would be some combination of the s, and k would be some combination of p and its complex conjugate. So that's how you can think of them, n equals 2 versions of s and p. So in addition to deforming by these scalars, we also have another scalar, which is the marginal operator. So we can deform the Lagrangian by a marginal operator times tau, where tau is just the complexified coupling, which you can relate to the Tuft coupling with this formula. So these are the different deformations you can consider. Now, one subtlety is that the sphere free energy is divergent in 4 dimensions. So not all quantities have well-defined definitions. But one quantity which does is if you take 2 derivatives of tau and 2 derivatives of mass, this is a finite quantity. And so this is the quantity we're going to consider in particular. And so just based on StatMech, if you deform a partition function by some number times an operator, and then you take derivatives of that number, it gives you integrated endpoint functions of that operator. This is basically what sources mean. And so because these taus are coupled to phi, and this m is coupled to s and p, if we take these 4 derivatives, we're going to get combinations of integrals of ss phi phi bar and pp bar phi phi bar. So this is the basic tool we're using. So how can we actually simplify these integrals now using supersymmetry? So the first thing we're going to use is that for any n equals 2 superconformal field theory and for any SUSY operator u, so let's consider an n equals 2 language, phi and phi bar, which are the bottom components of a multiplet whose top component is marginal. So for instance, in n equals 4 language, the top component would be this capital phi, and this little phi would be the bottom component. And so if you have an expectation value of any operators u and then an integral over phi, that's the same thing as just evaluating phi at the north and south pole. So basically, we can kill an integral if it involves this marginal operator. And so this is very nice, because originally we had integrals involving 2 phi's, and so the part of the integral that's integrating over the phi's, the integral just goes away, and you just evaluate the phi's at the north and south pole. So in particular, these little phi's are related to components of S, so we can relate SS phi phi bar and PP phi phi bar now just to SSSS and PP bar SS. So this is the first simplification. Then you can go ahead and compute the word identity that relates SSPP to SSSS. This unfortunately was not given in that paper by Korchemsky, so I just did it myself. And then you can write everything in terms of SSSS. And then after using crossing symmetry and the S4 isometries and a lot of hard work, you get this incredibly simple formula, which is that these 4 derivatives equal this simple integral. I mean, so this is a 2-dimensional integral, because you can see that it only depends on the magnitudes of this vector x. And so this integral, in fact, looks exactly like the integrals you get in basic quantum field theory when you're computing like a 1-loop diagram. And so this is super easy to evaluate. Okay, so now let's see what we're comparing it to. So we have a formula that gives the derivatives of the free energy to SSSS. Now can we get the derivatives of the free energy for the actual Lagrangian? Indeed we can, using localization. So this famous paper by Pestun, he computed the S4 free energy on n equals 2 star. He got the following n-1 dimensional integral, where the details of these functions don't really matter. One thing to point out is that we're considering the strong coupling limit, large n, such that instantons don't contribute. So this is a subtlety which would plague you if you were doing the finite Yang-Mills limit, but you don't have to worry about it for the strong coupling limit. So you can compute this to leading order in large n in a saddle point, and you get this answer, and this answer works for any lambda. So in principle, this interpolates from weak to strong coupling, at least at planar limit. We, in particular, are interested in strong coupling, so we furthermore expand this integral. This is surprisingly very difficult, but so you could try it yourself. It's very hard. and you get the following expansion. So actually, the lowest term here was given in the Russo and Zarembo paper, but to get the higher terms, the ones that involve zeta functions, we had to do that ourselves. And so this already has the expected answer, because you see that you have the zeta of 3, which is the famous zeta of 3, which shows up for r to the 4, and then you have zeta 5 for d to the 4, r to the 4. You have all these zetas that come from the standard string theory answer. Great. So now we have all the ingredients. So we have the derivatives of f in terms of SSSS. We also have derivatives of f in terms of a known answer. So let's just compare the two in order to fix the coefficients of SSSS. So we have one constraint. So that means we can fix one coefficient. And so in particular, we can get the r to the 4 guy. And after taking the flat space limit, this indeed gives the known r to the 4 guy in type 2b S matrix. So this is a precision test of ADS CFT beyond supergravity. We can actually do more, though. So far, we've just used CFT. But we actually know in the S matrix what d to the 4 r to the 4 is. It's some function of zeta of 5. So if we use the known string theory answer, so this is in the style of what Voshko did in his paper. So we can use the known answer to fix yet another term, because we have a second constraint. So this means we can go to the next order, which is lambda to the minus 5 over 2. And this is the answer we get. So this is the Mellin transform of SSSS. So the first term is tree level. So it's proportional to 1 over CT. This is the zeta of 3 term. And then this is the full zeta of 5 term by using both localization and the known answer. Great. In particular, you can extract the anomalous dimension. And this gives a prediction for the anomalous dimension given here. I should note that also the one-loop supergravity term has also been computed by these people, some of whom are in the audience. But this is beyond supergravity. OK, so far we've just discussed the strong coupling limit. We can also look at the very strong coupling limit. So recall that in that limit, Yang-Mills is finite, so instantons are going to contribute to the localization answer. So it's hard to use the localization answer because we just don't know how to do an n-dimensional integral with this incredibly complicated instanton function. So instead, let's only use the other direction, which is where we use string theory to learn about CFT. So we know that the answer in string theory at finite string coupling is this Eisenstein series. And so we can impose that on the CFT using the flat space limit to get the CFT amplitude expanded to this order. So this c to the 7 over 4 is the r to the 4 order. And so this is a prediction. So this, in a sense, is a non-perturbative prediction for Yang-Mills, at least. So in line with the title of this conference. And then we can go another step. So we know that this should be related to the free energy. And this is the answer from string theory. So if we then relate this to the free energy and perform an integral, you actually get the fairly simple answer. And so this is a prediction for the sum of infinite instantons. So the claim is that if you take the partition function, if you were to compute it at leading order in large n, and if you were to sum up all the instantons, then the answer should be this very simple Eisenstein series. And so this suggests that it should be possible. So hopefully some very smart member of the audience will be motivated to do this. Yes? Well, I'm going to talk about ABJM next. There is no Fermi-gas formalism in 4D. I mean, there is, for some chiral stuff there is. Yeah, but there's no Fermi-gas formalism for anything non-trivial in 4D, unfortunately. Yeah, so, I mean, it would be super great if someone could compute this free energy to beyond leading order in 1 over n. Because the more orders you could compute, the more I could fix with them. So this is another question which hopefully people will work on. Great. So one last thing we're going to say about n equals 4 super Yang-Mills is, so this is using this great paper by Alday, BC, and Perlmutter that came out recently, which is they were able to show that the non-analytic one-loop r to the 4 term, as well as the d to the 4 r to the 4 term, can actually be derived by knowing all the tree-level r to the 4 terms of form SQ, SQ, SS. So what this notation means is that SQ has dimension q. It's still half BPS. You can think of these as just the higher KK modes on ADS5. And so if you know all of these, then you can use that to construct the non-analytic terms. So they used that, as well as the relationship to the known string theory answer, as well as a conjecture about the functions that should show up, to have a conjecture for what this SQ, SQ, SS at r to the 4 should look like. And they were able to fix it just in terms of 2 q-independent constants, B1 and B2. And luckily, this paper came out as we were finalizing our paper. And so then we used our results, and we, first of all, gave a lot of evidence for their conjecture, because we found that their conjecture was true for infinite values of q, as long as B1 and B2 are fixed to certain numbers. So this doesn't prove the conjecture, but it makes it seem almost certain that it must be true. So we did this just by generalizing our previous computation to SQ, SQ, which I won't go through the details. And so now that you know B1 and B2, this means that you can actually compute anomalous dimensions of double trace operators to order CT to the -2, lambda to the -3/2. So this is beyond the planar limit, beyond supergravity CFT data. You can't do it for all spins, because these are just the non-analytic terms. And to get the lowest few spins, you need to also know the analytic terms. But you can do it for infinite spins. So still very nice. OK, so now we're done with n equals 4 Sebring-Mills. We're going to move on to ABJM theory. So ABJM theory might be a little bit less familiar. So there's two gauge groups, U of nk, and in principle, U of n plus L minus k. And it says Chern-Simons matter theory with matter transforming under these gauge groups. So we're not going to worry about this parameter L, because as long as L is much smaller than n, it has the same large CT expansion, where CT in this case is proportional to square root of kn cubed. So for simplicity, we're just going to set L equal to 0 and only talk about UN cross UN. There's two cases. If k is bigger than 2, it has n equals 6 supersymmetry with R symmetry SO6. If k is 1 or 2, then it has the maximal supersymmetry in 3D, which is n equals 8. We're going to discuss both cases. So keep in mind small k and large k. So for the n equals 8 case, the stress tensor multiplet is way simpler than in 4D. So again, we have two scalars, S and P. P is now a pseudoscalar, actually. Again, their dimensions are shifted by 1. So the lowest one is dimension 1, the next one is dimension 2. But now we don't have a marginal operator, of course, because ABJM theory is not a conformal manifold. So we only have two scalars. Similarly, for n equals 6, now the stress tensor multiplet is a third BPS. So we're looking at a 4-point function of a third BPS operators. There's a lot more operators, but we still only really care about S and P, although you should keep in mind that these fermions also exist because they're going to show up in one place. OK, so let's move on to the holographic dual. So the important quantity is n over k to the 5, which seems like a crazy quantity, but it turns out to show up in ABJM theory. So if this quantity is very large, then ABJM is dual to 11-dimensional M theory in ADS4 cross S7 mod CK, where the parameters are related as such. So unlike the n equals 4 Sebring-Mills case, this isn't a precise relation. This is an expansion in CT. So it would be interesting, actually, to get corrections to the ADS radius. So similar to n equals 4 Sebring-Mills, 1 over c counts both loops and higher derivatives. So this is somewhat analogous to the very strong coupling limit in n equals 4. And again, they're only distinguishable at low orders. So in the flat space limit, this is related to the 11-dimensional Planck length expansion. Now, if you let n over k to the 5 be super small, so the opposite regime, then if you define this Tuft coupling to be at leading order n over k, then ABJM theory is going to be dual to 10-dimensional type 2a string theory on ADS4 across CP3. And so in particular, we look at the Tuft limit where lambda is going to be large. And so then you can relate these parameters as such. And so now, just like in n equals 4 Sebring-Mills, c counts loops, lambda counts higher derivatives, and it's related to the GS and LS expansion. Finally, we can consider an interpolating regime, which is we let n over k to the 5 be some finite value, let's call it mu, and then as we let mu go from infinity to 0, we're going to interpolate from type 2a to M theory. So this is like a very weird limit you probably haven't seen before, but it's useful in ABJM theory if you want to interpolate. OK, so let's repeat what we did for n equals 4 Sebring-Mills, now for ABJM theory. So we can consider a 4-point function either with n equals 8 or n equals 6. They're very similar because they both have the same number of structures that show up. These are the tensor structures. In this case, we don't have such a simple answer for the ward identity. We can't just write it as some reduced amplitude. So we're just going to write it really in terms of these 6 structures, which I label by I, so these GIs. For each GI, we'll consider the Mellin amplitude, very similar to 4D. And then just as in 4D, we're going to define these MPs, with index I, which counts the degree. So now P is just literally the degree, because we're not looking at a reduced correlator. And again, we can use Joao's formula to relate ratio of these Mellin amplitudes to a flat space limit, which is going to be either 10-dimensional or 11-dimensional, depending on the specific theory we look at. But it actually doesn't matter. I mean, it's just the same factors in any case. OK, so now let's list the constraints we have on these Mellin amplitudes before using the Lagrangian. So as before, we have crossing symmetry. Now it's going to be a little bit more complicated because it's going to shift around these MIs because there's R symmetry indices. We have the superconformal ward identity. So this was worked out by Dolan, Gallo, and Sokachev in n equals 8. In n equals 6, we worked it out ourselves. As Shinan and Leonardo taught us, you can think of this ward identity in Mellin space as shifts in ST and U, because we're going to be working in Mellin space. So let's, for now, just talk about tree level. So again, there's only single and double trace operators. Again, double trace operators are taken into account by the gammas. Again, the single trace operators are just the stress tensor multiplet, so there's very few of them, just a scalar, a vector, and a stress tensor. One new subtlety, which is why I said we have to think about fermions a little bit, is that when you look at a 4-point function of half BPS operators, just by looking at the constraints of SSSS, that's enough to completely fix, that gives you all the possible constraints. But it turns out that when you look at a 4-point function of a third BPS operators, you have to work harder, and you have to look at 4-point functions of other operators in the multiplet. For instance, SS chi chi, where chi is a fermion in the stress tensor multiplet. And so only by looking at these other correlators and also imposing that they have the right poles do you actually get all the constraints. So this is kind of similar to the 3D n equals 1 talk, where we learned that descendants are very important. Because without these superconformal descendants, you would not get all the constraints. And this causes a lot of sorrows. Okay, so let's look at the allowed Mellin amplitudes that we get with these constraints. So this is similar to the table before. We have the usual r, r to the 4, d to the 4, r to the 4. But now there's more cases we're going to consider. So there's tuft scaling. This is analogous to n equals 4 Supergravity Mill strongly coupled, and it's exactly the same parameters because it's still type 2 string theory. There's finite k scaling. This is something we didn't have before in 4D. This is going to be related to M theory, and it's just an expansion in CT, and you get these fractional powers. And then there's the finite mu scaling, and that is actually analogous to the very strong coupling limit in 4D, and so you get the same powers of CT. And so eventually we're going to use this finite mu scaling to interpolate between this k scaling and this tuft scaling. Another subtlety is that depending on whether or not we have n equals 8 or n equals 6, there's different amount of Mellin amplitudes that we get. So in the maximally supersymmetric case, it's the same counting as 4D, as you would expect, because they're both maximally supersymmetric. But once you have less than maximal supersymmetry, there's now more coefficients you need to fix. So like there's 3 up to this order, and then there's 7, and they become 10. So it starts quickly proliferating. So it's much harder with just n equals 6. So some details about these Mellin amplitudes. Again, M1 just corresponds to the stress tensor multiplet superblock worked out by Sheenan. This includes all the poles, implying that the higher terms are just polynomials. Again, we can fix its coefficient just with the conformal word identity. And so in the n equals 6 case, because there's more Mellin amplitudes, we're going to need 2 constraints to fix it to order r to the 4. Whereas in the maximally supersymmetric case, you would only need 1 constraint. And so if you have 2 constraints, you can actually do a little bit more, and you can go all the way to d to the 4, r to the 4. So now I'm going to tell you what those 2 constraints are using the Lagrangian. And again, using the master form free energy, just like in 4D. So to describe this, let's consider an n equals 8 theory with SO8 R symmetry as an n equals 2 theory, which has U1 R symmetry, and the rest of the R symmetry, let's think of as a flavor symmetry, so SO6. Similarly, we can think of n equals 6 as having flavor symmetry SO4. So in the n equals 2 language, we can consider a current multiplet. So J is the current. We have a dimension 1 scalar J and a dimension 2 scalar K, very similar to in 4D. Again, these are related to S and P, if you think of it in the full supersymmetry. And again, we're going to deform the Lagrangian by a mass coupled to this J and K, which takes the following form. So one thing to note is that these flavor symmetries have a certain number of cartans. So SO6 has 3 cartans, and SO4 has 2 cartans, and that means there's 3 possible masses in the n equals 8 case, 2 possible masses in the n equals 6 case. Because remember, there's a trace here. So this is so these things really have indices I'm not showing, and this is really a matrix of masses. And we're coupling this matrix traced with these operators. So the first thing you can do is you can start by taking just 2 derivatives of the masses. And so this should be related to integrated 2-point functions, same reasoning as in 4D, which we know on general principles is proportional to CT, because they're all in the stress tensor multiplet. So this is a way of actually computing CT. Because unlike 4D, CT has a non-trivial expansion to all orders. And it's actually kind of interesting, because like in 4D, if you would have taken just 2 derivatives of the mass, you would have gotten something divergent, which you would have had to regularize. And after regularizing, you would have had just a trivial expansion, which has to do with the fact that CT in 4 dimensions is just trivially fixed to be n squared. But that's not the case in 3D. It's non-trivial to all orders in CT and all orders in K. Okay, but we want to do more. We want to look at 4 derivatives to get relations to a 4-point function. So one more comment is that both SO6 and SO4 both only have 2 quartic Casimirs. So this means that there's only 2 distinct ways of taking 4 derivatives. So this means that from the perspective of integrated constraints, you don't actually gain anything by having n equals 8 versus n equals 6, because in both cases, there's only 2 constraints. So that means for now on, let's just talk about n equals 6 in regards to these constraints. So you have these 2 constraints. In each case, taking derivatives of m plus or m minus, the 2 masses, are going to bring down powers of j plus or minus, k plus a minus, which is just different contractions of their indices in this form. It's the same story as in 4D. Now we're going to use a trick which is that every 3D theory with at least n equals 4 supersymmetry has a 1D topological sector, as originally shown by me, Silviu, and Ron, and then later also in a paper with Mykola Didoshenko. And in particular, under this correspondence, the 3D operator S corresponds to a 1D operator J tilde. And so what's useful about this is that if you have an integral, a 3D integral of ij plus k, under this correspondence to 1D, it ends up just becoming a one-dimensional integral of J tilde. But then what's even nicer is that this is a 1D topological theory. So that means that things don't depend on position. So you can just fix the positions of the operators to be any point you want. And so in particular, the integral is just completely killed. And so what ends up happening is if you're just taking a derivative of one mass, so that means you only have like either J plus or J minus, then all the integrals go away, and you get this very nice, simple, exact relationship between 4 derivatives of a mass and these functions G. Remember, G is just the coefficients of the different tensor structures. So just evaluated at certain values of U and V, like this. This might be familiar if you carefully studying my previous papers, because in previous papers, we also showed that you could use the 1D theory to get exact formulas for certain protected OPE coefficients, and you could then use those OPE coefficients to fix things in the large N expansion. And that's basically the exact same constraint as here. Because with this integrated constraint, again, there's no integrals. You're just relating it to these quantities evaluated at certain points. If you take mixed derivatives, this is a typo, this should be squared, then it's a little bit harder. Because in this case, we can only make 2 of the operators be one-dimensional and topological, but we can't make the other 2. Because when you deform by both n plus and n minus, that's no longer within the 1D topological theory. So in that case, you can fix 2 operators to be topological, but then we're going to be left with 2 other operators, which could be either SSSS or SSPP. So then we had to compute the ward identities relating SSPP to SSSS, which was very hard, but I'm not going to give you the details. And yet, surprisingly, after an incredibly complicated calculation, which if you saw the intermediate steps would terrify you, you get an incredibly simple answer, which is almost identical to the 4-dimensional answer. I mean, it's hard to even distinguish them. I mean, now it's just a 3-dimensional integral instead of a 4-dimensional integral, and slightly different powers of this 1 minus x and x. But like, this was completely surprising in intermediate stages. Like, in fact, in one of our earlier papers, we hadn't had such a simple formula, so we were numerically integrating these d-bar functions on a supercomputer. But like now we actually learned that we could do it analytically using this simple formula. Okay. Yes? Well, I mean, you can really fix the values of the positions to be anything you want because it's topological. So like this was just for convenience. It's like we could have fixed it to other values. They'll all give the same answer. Why not? I mean, I think originally we chose something like 1, or I think we originally chose half-half, which I guess was more symmetric. But then it turns out you could write it even simpler if you changed half-half to 1-4. So like, yeah, I mean, as long as it lies on the line, you can choose the points to be anything you want. Okay, so just as in 4D, now let's say what we know about this free energy from localization. So again, in 3D, it's been computed with localization deformed by mass in this famous paper by Kapustin, Willett, and Yakov. It becomes this 2n dimensional integral because there's 2 gauge groups, un, un. But turns out 3D is actually nicer than 4D in the sense that you could compute this 2n dimensional integral to all orders in n for any k equal or smaller than n using Fermi gas method by Marino-Putrov and in particular Nosaka. And the answer is always in terms of an Airy function, which is some complicated function. So, I mean, this should really amaze you because it's extremely rare in quantum field theory that you could compute non-trivial quantities to all orders in perturbation theory. This is every single order. Like, the only thing you're missing is non-perturbative corrections. But, like, it's so good that you can compare it to, like, finite values of n for n equals 1 and 2, and it's basically identical. So we use these amazing results from the Fermi gas method to fix the derivatives of these free energies to all orders in C, T, and K. So I'm just going to show the lowest few orders for simplicity, but we have all orders. And in particular, I'm going to show it for the case finite mu. So I could have expanded this in the Tuft coupling limit. I could have expanded this in the finite K limit. I'm just showing you the finite mu limit, because that's going to interpolate between the two. And so the leading term in both cases looks like tree level, because it's just 1 over C. And then this subleading term, you might remember that Ct to the 7/4 is the r to the 4 term in this funny finite mu version. Similarly, in n equals 4, 7/4 was the r to the 4 term for very strong coupling. So we get the expected r to the 4 term here. And then we get one term which has a zeta of 3, and then another term which doesn't have a zeta of 3, but which has a square root of mu. And so this is going to be very important, because you might recall that in string theory, we expect r to the 4 to have a zeta of 3, whereas in M theory, we don't expect r to the 4 to have a zeta of 3 because it came from one loop, r to the 4. And you're going to see that happen. In fact, we're going to interpolate between the two. Okay, so now let's combine this free energy expanded to all orders with the integrated constraints to actually fix the Mellin amplitude. So let's first discuss the finite mu case. Yeah? It interpolates between 0 and infinity. Yeah, so like in one limit it's M theory, one limit it becomes type 2a. Because like this mu is defined to be n over k to the 5. And if you just do the actual brane construction in the original ABJM paper, it turns out like that's the parameter. Yeah, in some senses, I guess you could say it's like related to the 11th direction, to the radius of the 11th direction. So you're making the radius big or small. You know, that's one way of thinking of it in CFT terms. So now we can show the answer. So we have two constraints because we had two combinations of derivatives, and for n equals 6, there was two terms we had to fix up to r to the 4. There was a degree 3 Mellin amplitude and a degree 4 one, and so we're able to fix both of them. We get the following very ugly-looking answer. It becomes slightly nicer if we first look at the mu to infinity limit. So in that case, the zeta of 3 term, if you now rewrite the variables just in terms of CT in this limit, so the zeta of 3 term is going to look like CT to the minus 2. And so that's what you expect from an order 1 Mellin amplitude, which in particular should also include non-analytic terms in ST and U, and we don't know the answer for that. So we're just not going to talk about it because we don't know how to fix it yet. And so we're basically ignoring the zeta of 3 term. But the other term becomes CT to the 5/3, which is the expected scaling for the finite k limit. And so here we have the finite k limit, which we're going to compare to M theory. And so in particular, if we take the flat space limit of this, we exactly recover the r to the 4 term in the M theory S matrix. And so this is actually a check of ADS-CFT to genus 1, because the tree level r to the 4 in M theory was derived from the genus 1 term in type 2a. And so this is the first check of ADS-CFT to genus 1 for local operators. And in fact, I would say is the first check of ADS-CFT to genus 1 for anything, because the other checks all involved kind of quantities that were trivially fixed. Like for instance, like when people computed Wilson loops, by with Drucker and Gross, it was related to an anomaly, and so it was kind of trivially fixed at leading order. And like other calculations involving the partition function, also you were basically just using tree level data. This is the first real check of ADS-CFT to genus 1. And you could say this was also checked in another paper of mine with Eric, where we did it from the perspective of the 6D theory. But in that case, we didn't use the master form free energy because we don't know what it is. Instead, we used the chiral algebra. Okay, so far we've discussed finite mu and finite k. Now let's look at the other limit. Mu goes to 0, so this gives you the Tuft coupling limit related to string theory. So now, remember there's two terms, a zeta of 3 term and another term. So the zeta of 3 term, the term that isn't zeta of 3 had this scaling. This becomes subleading in CT. And so, but let's keep it. So let's not throw it out like in the finite k. So here's the answer we get. So we get this lambda to the minus 3 over 2 term. This we expect to be r to the 4, where both Mellin amplitudes contribute with the zeta of 3 factor. And then at next order in 1 over CT, so this is the one loop order, we get a term which starts with square root of lambda, and then there's going to be subleading terms which don't have lambdas. So this might seem a little bit funny to you, because you would think maybe that the first term should just be 1 over CT squared. Like, what's the square root of lambda? What does it mean? So it turns out that the square root of lambda exactly corresponds to the analytic terms that showed up at genus 1 in string theory. So you might remember that when you look at genus 1 in string theory, there's analytic terms, which are polynomials, and non-analytic terms that aren't polynomials. So the non-analytic terms had different powers of string length, and so those would all correspond to lambda to the 0 here, which we're ignoring because we don't know what they are. But the analytic term, we do know what it is, and in fact, we can match it. And so now if you take the flat space limit of this and compare it to type 2a S matrix, we match both the r to the 4 term as well as this analytic genus 1 term. So this, I mean, philosophically, this is equivalent kind of to the M theory match. Both of them are genus 1. But this is somehow more explicit, because we're literally matching a one-loop term to a one-loop term. Which, again, this is the first real match of this in ADS-CFT. I should note also that in n equals for super Yang-Mills, non-analytic terms could also be derived from, but these are essentially fixed by genus 0, so it's not really genus 1. No, but it's not fixed by supersymmetry because we're using the Lagrangian. Like that's the difference. So like if you just had supersymmetry, that was my first set of constraints. And that's not enough. I mean, that gives you a certain number of Mellin amplitudes. So like if you just took any generic theory with a holographic dual of this amount of supersymmetry, you would be able to know the number of functions, but you wouldn't be able to fix their coefficients. Like the real meat of this argument is that we use the Lagrangian of the known theory, and that's what gave us these precise numbers. Well, no, because that's assuming there's only one theory which has that amount of supersymmetry. I mean, like what if there was 5 different n equals 8 theories? Like BLG theory, for instance. BLG theory is another n equals 8 3D theory. It's completely different from ABJM theory in general. It has a different Lagrangian. You could do this argument for BLG theory. And in fact, we did an argument like this for small n. But you get a totally different answer. You don't get zeta 3s. You don't get the right numbers. Yes. But I'm not sure that's true, though, because, I mean, like, that's assuming that there's only a unique theory, which, like, once you know tree level, you know all higher derivative corrections. But it's not obvious to me that that's the case. I mean, like, this is assuming that, like, there's only one theory which has, like, a holographic dual, and so once you know it's tree level, you know all the higher derivative corrections. And in some sense, you might say this is, like, assuming that there's a unique theory of quantum gravity. But like, I agree. But you could fix that without knowing the Lagrangian. So like you can fix the 2 PP ones, I mean, as Shinan did without knowing the Lagrangian. I mean, it completely follows just from supersymmetry. No, but I don't think so. I mean, when Shinan computed this, I don't think he used the Lagrangian. Sorry? Yes? You know, I mean, the original calculations did, but I think one of the things we learned from these new methods by Leonardo and Shinan is that you didn't have to do that. Is that, like, it's literally just fixed by having a flat space limit and supersymmetry. No, but the overall coefficient is fixed just by conformal word identity. I mean, the conformal word identity fixes the OP coefficient of the stress tensor multiplet to inverse CT by definition. I mean, in any theory, in any amount of supersymmetry, in any dimension. And so, like, that's just a definition. I mean, you can say what CT is, but like you never actually use what it was. Like you didn't have to use the fact that CT is a certain power of n or something. Like you can just fix that with conformal symmetry. You don't even need supersymmetry for that. Well, I stand by what I said, which is that at genus 1, there are analytic terms and non-analytic terms, and the non-analytic terms can be derived from tree level. Even within string theory, that's what they do. Like the papers by Michael Green, they don't need a genus 1 calculation to get the non-analytic terms. Like you can get it just from genus 0. But anyways, let's discuss this maybe at the end. Okay, so now let's also discuss n equals 8 supersymmetry. So in this case, remember that there was fewer possible Mellin amplitudes that you could write down. So that means if you have 2 constraints, you can go to one more order. In particular, you can go to the d to the 4 r to the 4 order. So for r to the 4, we get the same answer as n equals 6, which is to be expected because they're the same theory. It's just you're letting k be maybe bigger than 2. But now we can actually show that the next term vanishes. Now, this might seem like a trivial result, like, oh, it vanishes, maybe that was obvious. But that's not obvious. Because if you looked at the allowed counter terms, d to the 4, r to the 4 is allowed by supersymmetry. And it only vanishes due to this localization constraint. If you didn't have the localization constraint, you wouldn't have known it vanished. Similarly, in the context of quantum gravity, the reason you knew that this term vanished was due to using these dualities and relating it to string theory. If you were just given 11-dimensional supergravity and you were guessing what the counter terms were, you would never guess that the d to the 4 r to the 4 1 vanishes. So this is really a non-trivial check of eta CFT to 2 orders beyond supergravity, albeit at genus 0 in this case. Now we could do a little bit better. So just as in n equals 4 super Yang-Mills, we could use the known answer of the S matrix to further fix the CFT correlator. So we're going to do a similar story here now. We're going to use the known d to the 6 r to the 4 term in M theory to fix yet another term in CFT, which is the degree 7 one. And so we get this answer, these very complicated numbers. And so this is a CFT correlator, I believe, fixed to the highest order known yet beyond supergravity, so all the way up to c to the 7/3. And this is kind of like as far as you can probably get with protected quantities, because beyond d to the 6 r to the 4, things aren't protected anymore. One thing which would be very nice is, so this is just tree level. So the first term that would show up that isn't tree level is one loop, which is ct to the -2. I wasn't including that here. And that would be necessary if you want to say this is really a CT expansion to this order. So hopefully, just as Alday and people did in 4D, if they could do something like this in 3D, it would be greatly appreciated. Okay, so let's review all the various new results. So firstly was our new method, which is that we derived a relation between localization results for sphere free energies deformed by masses, which themselves are non-trivial functions of both n and lambda, known through localization. And we related them to an integral of single trace operator 4-point functions in ABJM and n equals 4 Supergravity mills. So usually we were relating it just to a 4-point function of stress tensors, but you recall that in n equals 4 Supergravity mills, we were also able to relate it to PP22, where P are these kind of higher rank KK mode generalizations. And so this is something which could be used in principle for any value of n and lambda. In this talk, I only focused on large n, but you could also use this for small n. Then we use this localization result symmetry in the flat space limit to fix CFT correlators in n equals 4 Supergravity mills in ABJM theory to various subleading orders beyond supergravity, including the analytic one-loop term in the Tuft coupling limit of ABJM. And then we matched it using Joao's formula to string theory and M theory, S matrix. And so we were able to recover the R to the 4 term. And in the case of ABJM theory, we were able to also get the genus 1 analytic term. And in the case of n equals 8 supersymmetry, we were able to get the D to the 4, R to the 4 term, showing that it vanishes. One thing I want to stress, which perhaps I didn't stress enough earlier, is that forget about actually fixing these coefficients. Just from a philosophical perspective, there is no way to define what the M theory S matrix is just using quantum gravity, because there's no world sheet. So the only way people define it is through type 2A, but that doesn't work because you can only use that to compute the lowest few protected terms. So like, even if you were the biggest genius at string theory, you would never go beyond D to the 6 R to the 4 for M theory. So this is actually the only definition of M theory, I would say, which is taking the flat space limit of ABJM theory. And so like the grander goal of our program is not just to fix some coefficients using localization, but it's to define what M theory is, and hopefully, once we learn more about ABJM theory using the numerical bootstrap, to fix the M theory S matrix to higher orders, thus defining M theory through the bootstrap. Finally, we also use known S matrices for M theory and string theory to fix more terms in the CFT correlator for those who are very interested just in CFT. So for example, using this wonderful paper by Alday and collaborators, we were able to fix the one-loop non-analytic R to the 4 term in n equals 4 Supergravity mills. I'm not opposed to non-analytic terms, so don't get me wrong. In a sense, they're way more useful because they give you all the spins except for a few. Their only drawback is that I would argue that they're not technically genus 1. Okay, so there are many future directions to these methods. So first of all, we could apply it for other dimensions where the mass to form free energy is known. So for instance, in 5D, this has been computed. And one could study correlators and holographic theories in 5D using it. Also, we could look at cases in 4D or 3D with less supersymmetry. So there's 4D n equals 2 theories, which have holographic duals. There's 3D n equals 4 theories that have holographic duals. You also know the mass to form free energy. You could do a similar analysis in that case. Also, we haven't used all the localization results. So we discussed deforming the free energy by a mass. I mean, firstly, in the case of 4D, we didn't even use all those constraints because we took 2 derivatives of mass and 2 derivatives of the Tuft coupling. We could have just taken 4 derivatives of mass. The reason why we didn't do that is because we honestly just don't know the localization result in a large n expansion, which seems like a trivial thing, but it's actually surprisingly hard to do. And so like that's a new constraint we could get. But even more than that, we haven't used the squash sphere. So the only other known independent constraint due to localization, which I think has even been proven in some cases, is you take a round sphere and you squash it, you turn it into an ellipse, and then you can take a derivative of the squashing parameter, and this is also related to integrals of 4-point functions of the stress tensor. And this is the case in any dimension. So we could do this in both 3D and 4D, and the expectation is that this additional protected quantity should be enough to actually fix the CFT all the way up to D to the 6 R to the 4. But we even have an expectation that it should be precisely enough. Because in the case of 3D, remember we needed 1 more parameter to go to D to the 6 R to the 4, and this is the 1 more parameter we would get. And so this is something we'd like to do in the future, so we'll be able to match all of the known M theory terms. Another thing which was missing from this talk was the one-loop non-analytic terms, which are very important. So in n equals 4 Supergravity mills, they were derived in these series of works, but it hasn't been derived yet in 3D ABJM or in any theory other than n equals 4 Supergravity mills. And so this is a big outstanding question, which hopefully people at this conference can work on. Lastly, and I think from the most exciting perspective, is that so far I've just been talking about protected terms. But there's a lot more in the universe than protected terms. There are infinite terms that go beyond the protected terms, and we'd like to learn about them too. But luckily, we have this wonderful method called the conformal bootstrap, which can teach us about non-protected terms. And so now that we have these localization constraints, which allow us to feed into the bootstrap exactly known quantities about theories, and quantities which are known as functions of all the important parameters, such as n, k, g, a, mils, we can feed these parameters into the bootstrap and then combined with those non-perturbative methods, hopefully solve these theories for any value of n and for any value of the coupling. And so in particular, I'm working on that now for n equals 4 super Young Mills, and the plan is to solve n equals 4 super Young Mills. Thank you. Okay, so to expand on my last comment is that so people in the Bootstrap community might know that there was a wonderful paper by Leonardo Rostelli and collaborators where they studied n equals 4 super Young Mills, but in that case they didn't have any known quantity which was a function of the coupling, and so their bounds only apply to the entire conformal manifold, which was kind of a limitation. So you can't study specific values of G Young Mills. With our new constraints, we can put into the Bootstrap exactly the value of G Young Mills, and we have many such constraints. So I only discussed one in this talk. But if you include the squash sphere and more derivatives of masses, I think we have something like 5 different constraints, all of which are functions of tau. We can just compute these things in localization. For instance, for small n, we can just do integrals. And then we're going to be able to put in these exact values into the Bootstrap, which it's complicated, but there's a known method of putting in integrals of a 4-point function into the Bootstrap. You just integrate block by block. And then we're going to then just numerically bootstrap. And I mean, this might seem like a very crazy claim that we could solve n equals 4 super Young Mills, but we've essentially already done this for ABJM theory. So we had a paper in ABJM theory with n equals 8 supersymmetry where we showed that the bootstrap bounds were exactly saturated by a certain OP coefficient, which we knew as a non-trivial expansion in n and k. In particular, k was fixed to be 1 or 2, so it was a non-trivial expansion in n. And so this like random curve was exactly saturated by our bound. And so then using extremal functional method, you can read off all the CFT data, which we did. And so we have a prediction, at least in ABJM theory, which you could think of as basically a solution of ABJM theory, at least for the low-lying CFT data, which the Bootstrap can access. And so I think it's quite reasonable that using this exact same method in 4D, we'll be able to get the exact same results. Yeah, I mean, we could look at any point we want. So like there's many things you could do. Like you could see the Konishi operator interpolate into a double trace operator. You could go from strong to weak coupling. You could look at it for like n equals 2, 3, and 4, and like see what the manifold looks like. Like anything you want to learn about n equals 4 super Young Mills. Yes? Sure. Yeah. So like a general limitation of the Bootstrap is that in principle you would have to look at all 4-point functions to learn about all CFT data. So like we are, I guess, limited to whichever 4-point functions we look at. So in particular, they would have to be half BPS 4-point functions. But you might recall that I was looking at not just a 4-point function of stress tensors, but I also have integrated constraints that work for 2 other half BPS operators in 2 stress tensors, of the form 2, 2pp. And so like in principle, I mean, it's probably many years down the road, one could even bootstrap 2, 2pp. I think the blocks were even worked out by Alday and some collaborators in the past. And then you could also look at the operators that show up in these other 4-point functions. Well, I guess for the specific case of 2, 2pp, it's a little bit trivial, because I guess the blocks are the same as 2, 2, 2, 2. But if you look at the cross channel, it would be really different. Yes? That's an excellent question. Like, in a sense, it's this is kind of a philosophical question. It's like when you have 2 theories that are dual at one extreme and another extreme, what goes on in the middle? It's like what happens to Schrodinger's cat when it's not dead and not alive? So it's like what does it mean when you're in between M theory and type 2A? When you're at like finite radius in 11 dimensions, like what does the universe look like? I have no idea. I mean, like in the CFT, there's a precise definition of this, which I guess is just the general idea that one of the nice things about ADS CFT is that you take vague questions in quantum gravity and you make them precise in CFT. So I guess you could just define it as the CFT definition. Yeah, it could well be. I haven't thought about it very carefully.